A couple of years ago, I created a matrix whose elements are functions. In this case, matrix omega 2 has single variable t, and the elements of this matrix are functions, single variable functions. When I created the omega matrix of functions, I targeted for CPU device. Now that I learned how to use CUDA toolkit, I would like to create matrix whose elements are functions of multivariables. How can we create matrix whose elements are functions of multivariables? If you watch throughout this video, you will be able to create matrix whose elements are multivariable functions for GPU device. Hi everyone, my name is Thomas Kim. Today is May 27, 2022. This is my 119th episode for CUDA, SQL, OpenCL, MFC. In this episode, we will learn how to use Lambda for GPU device for use with SDD apply. To follow my current session, please double-click this link. Please note that I updated C++ library extension today. So if you want to follow my current session, you have to update your C++ library extension copy. If you want to download complete source code, please double-click this link. By using this form, you have to expressly request a pre-copy of C++ library extensions. If you don't install C++ library extensions, you may not be able to follow my current and future sessions. To follow my current session, scroll down. In the previous videos section, please double-click episode 118, this link. I would highly recommend you to watch videos listed in this playlist. Otherwise, you may not be able to follow my current and future sessions. Show more. In the download source code section, episode 118, please double-click this link. Show in folder, unzip it, rename 119. Copy the folder, copy, paste it in your working directory. Now start Visual Studio Code. Select SQL OpenCL from folder 119. Select this folder. Click this button, lambda.cu. Hit enter. Ctrl V. I will close Getting Started and paste some videos for your reference. If you don't know how to use SDD tuple with SDD apply, please watch episode 115 because we will heavily use SDD apply and SDD tuple in this session. Now include quote period slash Ctrl Z slash include slash talkplay1 CUDA extensions HBP. I will make some room. talkplay1 stream print auto endl talkplay1 endl auto L value reference and L talkplay1 and L namespace TCE talkplay1 CUDA extensions. This namespace is defined in the file talkplay1 CUDA extensions. Now template, type name, func type, type name, return type, type name, ARG, types, void, global, process, lambda, return type, this is pointer semantic, result, func type, F, SCD, tuple, ARG, types. These are pointer semantic ARGs. Please note that this is device kernel code, CUDA kernel. Also, ARGs, this is tuple, element of type pointers. Here, unsigned int I block dim x times block index x plus thread idx x. We will do operation result I SCD apply F, then TCE, this is namespace alias defined here. Tuple ptr to reference. We pass ARGs, then index I, this index, then semicolon. We haven't defined tuple ptr2 yet. Here, include talk play fun CUDA extensions.hpp, Ctrl V. I will arrange side by side. Now, Ctrl Home, scroll down. In this section, here, we define tuple ptr2 reference. Template, type name, ARG, types. It should be callable from host, also from device. Auto, tuple ptr2 rep, STD, tuple ARG, types. This is pointer semantic, L value reference, tuple, unsigned int I. ARGs, this is tuple. So we accept tuple as L value reference. The elements type of tuple are pointers, and we pass I. I is unsigned int, as shown here. So we are calling this function from here. We return tuple ptr2 ref. We pass tuple I SCD index sequence 4. We pass ARG types. Please note that this is a type. So we have to pass an instance. We will create another function. This function here. I would just copy, paste it here. Now it has SCD size t ints. Here SCD index sequence. We supply ints. It should be expanded. I will put a line break here like this. Then return, it should be std tuple arg types, and we are returning reference like this. This is return type. So std get ins tuple. Please note that each element of tuple is pointer, so we can extract ith element of tuple. Then we have to expand, because ins is parameter fact. We have to expand. I understand this is quite complex. I will arrange like this. So from this function, we indirect our call to this function. This function returns tuple of reference. So tuple from pointer to reference. We accept tuple with elements of type pointer. We accept tuple whose elements are of type pointers. Then we return a tuple whose elements types are reference. So we can apply F through tuple ptr2 reference. Now let's learn how to use std apply with tuple ptr2 reference. Void test apply tuple ptr2 reference. Int main, copy this function, copy, paste it here. We define a lambda function f. It should be callable in the device code. Auto x, auto y, semicolon, return x times y. We made a very simple lambda for use in GPU device. Context per std size t n. For simplicity, I will set it to 10. Auto xx tce malloc device plot n. I will copy and paste. This is yy, this is rr. std array plot n x. We initialize 10 elements, 0.1 f, copy, paste, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, semicolon. I will simply create y, tce, copy to device from host. xx is device memory, x is host memory. Copy, paste, y. Now we are calling process lambda kernel. I will make it very simple kernel execution configuration. Then we pass rr get rr represent return type result. Then f. This f is lambda defined here, represent func type f. Now we pass tuple like this. std tuple xx get yy get semicolon. Please understand that malloc device is defined here or malloc device. Here it returns unique PTR. Okay, so we have to extract pointer from unique PTR. CUDA device synchronize. Now auto RTC to host array. We pass N, then RR. RR represent the result of our operation. Print result R and L. Now start command prompt. CD 119 Advanced Recursion NVCC SED C++ 17 ON.exe Extended Lambda EXPT Relaxed Contextful XPTX AS minus suppress stack size warning. The source file is lambda.cu. Lambda.cu. Hit enter. CLS N. So we passed X and Y to this kernel lambda by using process lambda CUDA kernel. Some of you probably wonder why I use this approach. Suppose our function is more complex, then we can change our lambda function on the fly. Then create set also jet, then we copy jet to device memory. We pass jet get. We haven't changed anything in the CUDA kernel, but still it works perfectly. CLS N. We don't need to concern CUDA kernel. All we need to concern is our lambda function. This enables us to create matrix whose elements are functions with multivariables. That is, we can create arbitrary matrix whose elements are functions with multiple independent variables for CUDA device.